parameter 1. So again, you see the comparison. You see, it's a whereas so this is a discrete distribution. It takes the values 0, 1, 2, 3, etc. with certain probabilities. So probability x equal to n is e to the power minus n 1 divided by 1 by n factorial. And you see that has a nice continuous distribution everywhere, whereas this is something else. It has a discrete point spectrum.
You add disorder.
So sudden change. No? So like here, you see you make one small change there, and the whole density has changed completely. And here, from continuous, it has become discrete. Okay.
So under perturbation theory, say change a little bit, change epsilon.
Yeah, that is what they study all the time. Yeah. So they change this one, add something in the diagonal. So here also they add something in the diagonal. So we'll see how it changes, the spectrum changes. Now that is the other amazing thing. See, because all this they actually apply it in physics to talk about the spectrum, right? Various conditions where so physically observable things. So they need to study the spectrum. Okay, so there are examples. There's another thing I want to say. See, this is hard to work with this kind of things. With this kind of tri-diagonal things, like with notation. How do you multiply things? If you have two such things, like if you want to compute a square, what happens? It is very difficult to keep track of the things. But physics people have various tricks. So you get this operator. So this is called the number operator. So 0, 1, 2, 3, etc. The diagonal. So even here itself I can say this way, like this is sum of say a0, a1, etc. Plus this one b0, b1, etc. and b0. So the diagonal things, the lower diagonal, the upper diagonal. Okay. So it is this is what we call the quantum decomposition, because this is the random variable you had. Okay, you can start with any measure mu and you get this tri-diagonal form. Okay, in a canonical way. Okay, because you start with the constant function 1 and you do it in a natural way. And this is a kind of operator which the en goes to an times en, right? So what we call a conservation operator. So this is an annihilation operator. You know, the basis vector en goes to something times en minus 1. Okay, so this is annihilation, this is conservation, and this is creation. Okay, this is creation, annihilation, and this is conservation. Means the en here it goes to some constant times en, here it goes to constant times en minus 1, and here it goes to constant times en plus 1. Okay. So, and in physics it's very natural to break up things like that, and all the time you have this kind of creation operators, annihilation operators. So as KRP calls them as the Trimurtis. So Brahma, Vishnu and Shiva. And so this is the quantum decomposition, okay, of classical random variables. It has to be quantum, you see, because these things don't have any meaning in the classical setup. Because there are some operators, and even here, see, they are not even self-adjoint operators. Okay. So only this one is self-adjoint.
Some.
Yeah, some is self-adjoint. Okay, so there is some trick I want to put there. This n, you take, this is the number operator. Okay, so because you can see n of en is n times en. star, the adjoint of this, which is the creation operator. Okay. L star. Okay. So which is the you know this. This is the isometric. This is co-isometric, and the standard unilateral shift, you might say. And but this is an unbounded self-adjoint operator. Okay. So these things help us to do the computations. Commutation relations. This is the commutation relation between n and L. So n L equal to minus L. So what does it mean? So that is NL minus Ln is minus L, I want to say. So you apply it on some En. Okay. So then gives you n. L of En is En minus 1 minus, you have to be a bit careful when in the probability n equal to 0, but it will work anyway. N of En is NEn. So this is n minus 1 En minus 1 minus, this is n times En minus 1. So this n cancels, so it will get minus En minus 1. So this is minus of L here. Okay. So I have this n comma L. So that is NL minus Ln equal to minus L. Or this is same as saying n plus 1 L equal to Ln. Okay. Now you see what happens. Once you have n plus 1 L equal to Ln, so what is Ln square? So Ln square, so Ln is n plus 1 L, then n, then again n plus 1 comes, so this becomes n plus 1 whole square L. So if you, whenever you take n from this side to this side, n becomes n plus 1. Okay? So Ln is n plus 1 L. Ln square is n plus 1 whole square L. So if I have any function of n here, okay, L, any function here, g, this would be g at n plus 1. Okay. This is a relationship here. Okay. So with this kind of things, so now you have to deal with just functions. Okay.
So G is any continuous?
G is a function on numbers, right?
Right, okay.
So with this, I can even write this A as, so that A, what we had there, it is a function like A of n, okay? Because A0, A1, it is A of n, right? So this is A of n plus I have to be careful. So I want to write this. There might be a mixing of one index. Okay? So you may have to shift it by 1 bit. Okay? Or you may write it on this side. LB1. I can write this. So that A I can write like this. Okay? So once you have this way, it's very easy to do the computations. If I want to compute A square, you just multiply it out, and each time you use this property. Okay? And terms of this using these commutation relations. Okay. So we don't do the computation directly multiplying that, but with this kind of formula. So this of course you have to keep in mind that this is n is an unbounded operator, but we work only on this domain, the linear span of EJs. Okay. So there is no problem. We can do all these computations. Okay. So now when with the accordic comes, what we want to do is the multivariable version of this. Okay. So that is, here we have done it with one self-adjoint operator. That is one random variable. If you have say t random variables, okay, x1, x2, xt, then even the theory of orthogonal polynomials, there is hardly any theory exist. It doesn't exist. People don't know what to do. Okay, because you start with one, then you have two things, say x and y, and then you have various things and how to order them. There is no nice recurrence relation, nothing. How to work with them, we don't know. But if you are seeing from this point of view, then things become easier. What you do is you start with constant 1, then you multiply. So you have say n operators, say a1, a2, ad. So then you apply that on 1, so you get some d-dimensional space maybe. So what you get is a kind of grading. The whole space gets divided into initially c times e0, direct sum with some space, direct sum with another space, direct sum with another space of different dimensions, instead of saying just one order. Okay. So whereas people are looking for some recurrence relation 0, 1, 2, 3 like that, instead you have different dimension spaces. Okay. And the translation moving back and forth, this annihilation creation takes place on different spaces. So this becomes like Fock space. So it is exactly like Fock space. So we can bring in the theory of Fock spaces, okay, and work with that. So only thing is these things. What is the inner product here? What is the inner product on the second space? And such things one has to work out. So what we call as interacting Fock spaces. You have various creation operators here, annihilation operators going back, while one has to get the corresponding commutation relations. So one can abstractly define things, but then to get this, say d commuting random variables, what is the relationship you need there? So those things one has to work out. So some things I think Accardi and his collaborators have done, but it's mostly incomplete because the theory of orthogonal polynomials itself is very incomplete for the multivariable version because people are not clear as to how to go about it. Because it is difficult to get any kind of recurrence relation. But now you know that you have to use this theory of Fock spaces. There things look much better. One might be able to organize things much better with this. So that is the idea.
Multivariate normal is known, for example, in this world.
Yeah, but there are some problems, some things which are not clear. So I think when Accardi will tell you. So means one can write down the things, but there are some questions which are unclear.
Commuting, decommuting self-adjoint operators, you have the joint functional calculus, right?
Yes, yeah.
That we can probably use that to.
Yeah, you can use that.
We were doing functional calculus, right?
Exactly. But then, this is the initial space. Okay, you start with the constant function 1. Okay, but then you will need a two-dimensional thing, or d means d-dimensional things. Okay, so then you apply, you get some d-square dimensional things, right? Because it's the multiplication by say x1, multiplication by some x2, xt. Then you multiply again by this space, so you will get xi, xt, some d-square dimensional space. Okay, so then you have the things going between d dimension and d square and d square d cube, going back and forth, right? So what you need is operators. Okay, instead of this kind of constants, you need operators. So this tri-diagonal thing gets replaced by operators. Okay, each time you have an operator from some what we call the grading, some k space to k plus 1 space. You can say k particle space to k plus 1 particle space, which have different dimensions. And so one has to work out the whole thing, whatever we did, which is easy for constant things. So it has to be done for when you have block operators. And and then you can abstractly write block operators like that, when all of them will not give you classical D random variables, because final random variables which you get should be commutative, right? So that commutativity will put some restrictions as to what kind of tri-diagonal blocks you would get.